go back and start over. At least you can hear me. Okay, I'm going to leave this on the board for just a second. Hope you got those written down. If not, I'm going to go back to it. I'm going to flip that there and here. It's already in here, so things I do for y'all. Huh? Well, you know, y'all are guinea pigs. I'm guinea pigs on this too. I'm a guinea pig. Now next semester, it'll be a whole lot better because I won't have to deal with half the stuff I've been having to deal with. And now I know how to fix the auto do-jigger.
Screen rotate.
Yep. And I have a mouse, and I have a hard drive, and I have a keyboard. I just have all kinds of stuff. So
It seems like it would be nice when as long as it works properly.
it does, but it has its hiccups. But Tri-County Tech, I'm on a committee for Tri-County Tech to make all classrooms, or at least every classroom on every floor of every building, have a front row that's got everything on it that's needed to do what we're doing here. So I've kind of helped start this, because nobody does it on campus with me. I mean, on all three campuses, I'm the only one. And I'm halfway doing it. I'm trying the best I can. All right, so here's your problems. And what's the first one? Well, this is x to the negative 3 plus 4 plus 7, which is 1 plus 7, which is x to the 8. This is x to the 4 minus a negative 2. Now notice what I did there. What did I do?
You're on parentheses.
Why did I do that? Because the negative will screw you up. So make sure you do not say, oh, well, that's 4 minus 2. Because that's what students do. They say, okay, 4 minus 2, the answer is x to the second. Wrong. It is not. It is x to the what? X to the 6th. So go ahead and erase. Because some of y'all put x to the second. That's not right. This one, x to the what? X to the 6th again. Why? Because negative 2 times negative 3 is x to the 6th. Now, some of y'all are saying, well, Hubert, isn't there a rule about negative exponents? Yeah, I haven't got to it yet. You'll get to it. I'll get to it in a minute. Don't steal my thunder. All right? So, what is 2 minus a negative 1? X to the 3rd. What's 4 minus a negative 2? I'm sorry. It'd be 6. You're right. I couldn't hear you. Now this one you can do two different ways. This one you can distribute using the power rule first and then do the quotient rule, or you can do the quotient rule first and then do the power rule. You will get the same answer if you do them both correctly. Notice I said if you do them both correctly. All right, what's 4 minus 3?
1,
So that'd be x to the first. And 6 minus 4?
2,
Raised to the 4th power, and that'll give us what? X to the 4th, y to the 8th. I don't know if he said he text. We're going to take it easily. Okay. All right, so that'd be x to the 4th, y to the 8th. All right, which leads us to the next two. The next two properties. The next two properties, number 4, is called the inverse rule. Now the inverse rule is the rule we need to get rid of negative what? Exponents. We don't want negative exponents. Now, did I say anything about scientific notation? No. Scientific notation and negative exponents, two different things. So let's not even talk about scientific notation because that's another animal. We're talking about just regular exponents on a variable or on a number. We're not talking about scientific notation. Scientific notation is the only place where negative exponents is okay. Now, some cultures could care less about negative exponents. And the reason I tell you that is I had a teacher one time for a short period of time, for about 2 days, because I dropped them, because they were from Asia. Has any of you ever had an Asian teacher? They hate America. Why are they here? Leave. All right? Now, they have a very, very strong work ethic. All right? Americans do not. I'm sorry, some of us do. Some of us grew up on a farm. Some of us grew up in the industry. Some of us grew up working real hard. And some of us know how to work. But some of us don't. But Asia, Japan, and China predominantly, they think we all sit around and eat potato chips and watch TV. That's what they think of us. And if you ever have an Asian instructor, they will insult you and insult the country that you live in and insult the country that they came over to get educated in. Yes?
Not to sound like a smart ass, but they also think we're extremely violent because of the media that we broadcast out.
Yeah, and we're racist and we hate each other. All right? But all the Middle Eastern people think that we're infidels. So, we're just might as well shoot ourselves. I mean, but I'm serious. If you ever have one, I mean, some of them, now I'm not saying that's all, but I do know that the Asian teachers that I have had, they were rough. They were rough on us Americans, lazy Americans. So I dropped. But they don't care whether it's a negative exponent. That teacher, she would put a negative exponent and keep on going. She wouldn't even think about making it positive. So it's not detrimental, all right? It's not detrimental that you have a positive exponent, but in good old US of A, we like to keep it positive. Just like our variables. We like to keep our variables positive. So I'm telling you that, not to condemn Asians, not to condemn Middle Easterners. I was being facetious. But some cultures don't care about the negative exponent. So, the rule is 1 over x to the negative n is equal to x to the n over 1. And x to the negative n over 1 is equal to 1 over x to the n. So if you want to make a negative exponent positive, what do? You flip it. Now I'm going to show you an example of this, and I'm going to show you the shortcut version, and I'm going to show you the longhand version. Let's do an example like, and I'm going to kind of throw a not hard example, but I'm going to throw a non-easy example on the board because I want to show you how this rule is used. Let's go with x to the negative 2, y to the negative 4 over z to the 4th. Now that's an example of negative exponents.
So if you flip it, wouldn't the z become a negative exponent?
Well, you wouldn't flip the z. If it ain't broke, don't fix it. And that's one of the things I wanted to say. If you have a positive exponent, you just ignore it because you don't want to mess with it. Now, what I tell students to do, if this is your first time dealing with the inverse rule, break it up, no sneezing, break it up as x to the negative 2 over what? 1. Y to the negative 4 over 1. And 1 over z to the 4th. And now what do you do to the ones that are broke? You fix them. So what do you do?
1 over x squared
Yep, good. 1 over x squared.
times 1 over y to the 4th
1 over y to the 4th.
times 1 over z to the 4th.
Miss Rose likes to use my shortcut, my Hubertisms. So she's already used to using them. All right? And that's the putting it over 1, putting it over 1. That's as easy as you can get. Now that's the longhand version. That's if you've never seen the inverse rule before, or if this is the first time you've seen the exponential laws, this is what you want to do with a problem like this. Okay, so your answer comes out to be 1 over x squared, y to the 4th, z to the 4th. That's your answer. Now, how do you do it shorthand? Well, shorthand, you just take this and do what? Draw an arrow down there, draw this, and then you get the same thing. Some of you may have had an algebra teacher that says, take it downstairs. You ever heard that before? Or take it down below, or take it above, and they just draw the arrow. Well, the long version right here tells you, this right here tells you how this is so. It's what's behind the shortcut. And that's the inverse rule. Now the next rule I'm going to show you is not a rule that's used a lot, because it's kind of a rule that you can use it when you want to. And it's called the inverse power rule. Now, do not get the inverse power rule mixed up with the inverse rule. It's a totally different animal. It's the same thing as a cat versus a tiger. They both have 4 legs, they both have a tail, they both are a feline, but they are not the same thing. All right? One weighs 500 pounds, the other one weighs 10, 11 pounds. Or some of y'all's 25 pounds because they eat potato chips and watch TV all day. Okay? And they don't live in Asia. All right, so you got the 2 different animals, but they have the same characteristics, but they're 2 different animals. The inverse power rule is used when you have, and I'll put it in green, in red, when you have a negative exponent outside parentheses. It's not used. Some people go ahead and use the power rule to get rid of the parentheses, and then you just have a regular exponent. So this is an optional rule. And it basically says that if you have x to the n over y to the m raised to the negative z power. So I have a negative exponent on the outside of the parentheses. Now, how is this different from the inverse rule? Well, the inverse rule, there is no parentheses. So when you have the parentheses, you have something quantity to the negative z power. That's a totally different animal than what we did before. Now, the reason it's different is if I flip what's on the inside right here, I turn that variable positive. Now, a lot of people say, well, I thought you said, well, that's a different rule. This is inside parentheses. The one we had before, this is not inside parentheses. This is a cat. This is a tiger. It has the same characteristics. It has a negative exponent. That's the only thing that's similar. So I'm going to flip what's on the inside. That will give me y to the m over x to the n raised to the positive z power. Now, the first question I get when I show you this is, why didn't the y to the m, why isn't that y to the negative m And why is it x to the n, x to the negative n? Because this is in parentheses, and it's a different problem than what we did before, the inverse rule. So all you got to remember is when you got parentheses, this doesn't change. This does. Now you can use this if you want to, because a lot of people do this. This is called the inverse power rule. And some people go this route. Some people just use the power rule. And what would that give us? X to the what? Negative Zn over x to the what? Or, sorry, y. Go back.
Negative Zn.
Y to the what?
Negative Zm.
Negative Zm. And then what would I do? Flip it and make them positive. And then you get the same thing if you did this. So both of these answers will give you y to the Zm over x to the what? Zn. Whichever one you do will give you the same answer.
Would it be the same if you wrote it y to the m, ymz, and x?
Yeah, same thing. 2 times 3 is the same as 3 times 2. So z times m is the same as m times z. Now there's an additional rule I'm going to show you, because those of you in 110, those 4 students, you're going to see this again. Those in 120 and 103, you're not going to see it very much. And that's called rational, and I guess this is number 6,
Yes.
rational exponents. And I don't use x and m's on this one. I use a standard radical that you're going to see, and that is the square root of, I forgot what x to the third. That's what I use. Okay? The square root, or the square root of x is what I use. I had a brain bubble there for a minute. There we go. The square root of x. Now, somebody tell me what's missing. There's 2 things up there that are there, but you don't see them. Somebody tell me what they are. Oops.
A 1 in the front and a 1 behind the x.
Well, 1 behind the x, well, 1 right here, and I'll make it blue. Well, that's interesting. Make that blue. There's a 1 right there. And what else? There's a 1 in front, but I'm not talking about that. Somebody tell me what else is missing that's there. What's in front of the radical, or up in the top of the radical, if it's not there, what's this assumed to be? A 2. Right here. Okay? If you have a radical, and you just got a radical sitting on your test, that is assumed to be a square root. Okay? If there's no number in the top, that's called an index. Let's write that down, index. Index. That 2 is understood to be a 2 if you don't have anything in front of it. Now there's a 3 there, that's the cube root. If there's a 4, is there a 4 there? That's the 4th root. There's a 5 there. But there is no first root, because the first root of a number is that number. So you don't need the first root. This, everybody knows what this is called. What's that 1 called? An exponent. Anytime you have a radical, you can write it as a rational exponent. Now, for those of you in the sciences, you're going to be seeing this a lot in calculus because there is no such thing as a radical in calculus. Radicals and calculus don't mix. You always rewrite it as a rational exponent. So you're going to be seeing it. And this is what you do. X to the 1/2. And that's exponent over what? Index. Remember that. Exponent over index. So let's throw some examples up here. The square root of 4 is equal to 4 to the 1/2 power. The third root of x to the second is equal to x to the what? 2/3. The square root of x to the third, the square root of x over y is equal to x over y to the 1/2 power. So anytime you want to take the square root of something in your calculator, get your calculators out if you got one. Raise it to the 0.5 power. And it's a whole lot easier to do that than find the radical sometimes. So hit 25, x to the y, or a caret symbol, 0.5, and see what you get. What do you get?
Oh, I did my own.
Did you mess that up?
I messed that up.
Good
I don't
gracious
use the
alive.
calculator. You should be happy.
I know, I am happy that you don't know how to twirl it around like a basketball like some of the students that can't make change for 6
He
cents.
says he's not sure. He says you're not.
Caret symbol looks like a
Okay.
rooftop, is one of my high school graduates said. That's a rooftop. No, it's a caret symbol. C-A-R-E-T. I think that's how you spell carrot. I mean K-A-R-E-T. Caret symbol looks like this. X to the y is also on some calculators, and y to the x is sometimes on calculators. Those are your 3 exponent keys. So take 2096 and raise it to the 0.5 power.
Is it to the point what?
Huh?
Raise it to what?
To the 0.5 power.
That's a very big number.
Mm-hmm. What is it?
45.782.
I'm sorry, what?
45.7820925.
Okay. So 45.082 is 45, close to 45. So make sure you know how to use your rational exponents. And that's mostly for you science people that are going into 110, 111, whatever y'all are going into. And that's how you use your exponential laws. Now, let's look at some problems that you have in some of your homework.
And what section is this?
This is 10.1. Now, I just went over your exponential laws because we're going into radicals and that's what we're going into. All right, so for I can't talk. A while back, I told you that you need to know your perfect squares and your perfect cubes for your shortcuts. Remember me saying that? Well, you need to know them now again. I'm going to just pull up my handy-dandy Excel spreadsheet, and I used to be able to do this real quick in the old Excel, but the new Excel, I can't do it as easy. This is how I did it. Let's see, I did 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oops. 10, 11, 12, 13, 14, 15. I tell students to go up to 15. And that's up to you if you want to go up to 15, but that's what I tell students to do. And I make these a little bit bigger so you can see them. And I'm going to make them all bold so you can see them even better. I like Arial, so I'm going to do Arial. Y'all have a favorite font? I have a favorite font. Mine is Arial because it's nice and neat. All right, so x squared, x, and I'm going to put caret symbol 2, means perfect square, and that's going to be equal to this raised to the second power, and then you just copy that down. There we go. And then the next one is x cubed. And then that's going to be equals this raised to the third power. I'll do the first two for you, 0 and 1. There's those numbers, and you can go up as many times you want to. X to the 4th. This is a nice little sheet to have, like on the inside of your notebook or somewhere where you do homework. It's a nice sheet to have. Again, I'll do the first two for you, 0 and 1. I had a neighbor call me up when their daughter was in algebra. She called me up and said, "I'm mad." I said, "What are you mad about?" And she said, "This calculator won't work." Have I told you the story? Have I told y'all the story? Yeah. Well, anyway, she was mad because she couldn't get 1 to the 29th power to come out right. How do you tell your neighbor that she's stupid? No, I'm just kidding.
Operator error.
Yeah, operator error. So you're not typing it in correctly. No. And x to the 5th, I usually tell students to go to x to the 5th. Because most of your homework problems are x to the 5th. Now, why am I showing you this? Because they will come back to haunt you if you don't know them or if you don't have them written down. You don't need to memorize them, but you need to have them handy because some of these numbers are going to keep popping up in your homework problems. And when you're talking about radicals, the first thing you need to talk about is the index. So there's your handy dandy perfect square card, and you know make it on your own. And I'm just last night days in a row. You know, you don't make shut up. All right, so that's something to help you out. Now, why do you need to know this? Well, when you're talking about radicals, let me ask you a question. Some of y'all may remember that when you go to a hotel, what do they used to have on every single floor? Some of the older hotels still have it. But what do they have on every single floor when you get hungry at the middle of the night or you get thirsty? What do they have? A snack machine and a Coke machine. Now that's the older hotels. What do they have now? They have a little canteen down in the lobby, and they don't have drink machines on each floor. They use that room for more rooms. But anyway, let's say you're at an old hotel and you want to get a drink. And here's the drink machine, and here's the snack machine. And drink machine it's an old drink machine because you're at an old hotel. And it only says quarters, dimes, and what? Nickels. Quarters only. Okay? You have just been dictated what you have to think in terms of. Right? What do you have to think in terms of? You got one that says quarters, dimes, and nickels, and one that says quarters. What do you got to think in terms of?
Quarters.
Quarters. Why?
One machine takes only quarters.
Because one machine is dictating what you need to think about. Well, what about the dimes and nickels? Well, yeah, you can have dimes and nickels if you want to, but you're going to go hungry because the snack machine just carries quarters. So, you got to go down and you got a $5 bill. Well, if you got a $5 bill, you're going to be hungry and thirsty. Why?
It's not quarters.
Because you got to have quarters. So you got to go down to the front desk and you got to get quarters. This machine dictates what you got to have. What the heck does that have to do with radicals? Here's your radical. This guy right here dictates what you got to think in terms of. It can be a square, it can be a cube, it can be a fourth root, it can be a fifth root. If you're talking about a square root, most of us know how to deal with square roots because we know our multiplication tables. But if you're talking about cube root and fourth root, that's when we start getting flaky because we don't think in terms of square roots and fourth roots. Now let me give you an example. What is 9 or 8 plus 1? What's 9 plus 1? Actually, 9 plus 1 is 0.
Mind blown.
What are you talking about? It's called combinatory mathematics. All right? What base system do we have? We have a base 10 system. That's what we think about. 1, 2, 3, 4, 5, 6, 7, 8, 9. I'm sorry. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we go back to 0. But to keep things from being complicated, we don't call it 0. We call it what? 10. We'll go 11, 12, 13, 14, 15, 16. Then we go back to 0 and call it 20. So 9 plus 1 is 0 in the mod 10 system. What about the mod 4 system? 0, 1, 2, 3, 0. So what's 3 plus 1? 0. 3 plus 1 is 10 again. And you can do that all day long. It's for codes. Code break. All right? Now, that is what this is. And if I tell you to add 9 plus 1, you're going to say, okay, well, that's 10. But if I tell you to add 9 plus or 4 plus 1 in a mod 5 system, you're going to say 0. All right? I'm telling you what to think in terms of. Some of you computer people, why do you have to think like that? Because you're not talking about a base 10 system in computers. You're talking about a hexadecimal. You're talking about a quadradecimal. You're talking about thinking in terms of different set decimals. Oh gosh, hecadecimals. You're talking about reading all kinds of different languages. All right, so you need to think in terms of the what? What's in that red spot?
Index.
The index. Let me show you a quick example. The square root of 9 is what?
3,
The square root of 16 is what?
4,
The cube root of 8 is 2. All right? I changed gears on you, didn't I? You have to go back and you have to say, well, wait a minute. There ain't no square root of 8. Some of y'all say square root of 8 is 4. That's what y'all will do. No, it's not 4, it's 16. All right? So I just changed gears on you. And if I say fifth root of 32, I'll make smoke come out of your ears. The fifth root of 32 is 2. And you have to think in terms of a square root, a cube root, a fourth root, a fifth root. Now, usually you don't go past 5 when somebody's asking you about the perfect root. What is a perfect root? It's the number that you multiply by itself that many times to get the big number. The perfect root of 25 is what? Positive or negative what? 5, Hubert. That's right, class.
So how do you figure that out?
You know what?
Oh, you know your.
2 times 2 times 2 times 2.
Yeah.
And that's why that little chart that I made is so helpful.
I was gonna say, so when you're presented that problem, how would you know how to figure out the answer to that was 2?
You would just take 2, 2, 2, and 2, and 2. You got to multiply something by itself 5 times. So let's start with 1. 1 times 1 times 1 times 1 times 1. That's no help. That's 1. 2 times 2, that's 4. 4 times 2 is 8. 8 times 2 is 16. 16 times 2 is, it's a miracle. Do the same thing with 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. 81 times 3 is 243. And the more you do those in your head, the better off you are in this chapter. So what's the 4 through 16? 2. Y'all want me to put that thing back up? There you go. Usually people go, will you put that back up there? Yeah, be glad to. You might want to write down those first 5 lines. I'm looking them all. I'll ask you when it's coming. Let me ask All right. So what's the 5th root of 1024? 4. Now you can do this on your Excel spreadsheet. You want to take a few minutes, print it out, put it on the front of your notebook. Especially if you're going into 110 or this chapter. Like the chapter test, I would have that on the front of your notebook or in front of something. Okay? Now, let me go to the text, and that's what we're talking about right here with the square roots. Now, always remember that your even root, if you have an even index, there's a couple of rules about an even index. And what is the rule about an even index? Anybody know it right offhand? Is that Logan? Let's see who it is. Even index, you cannot have a what in the, you cannot have a negative in the even index. You need to write that down.
So it's not a negative exponent. What is that called? Negative. You can't have a negative what?
Negative under the radical. Sorry. I'm having to arrange transportation. All right. Now, what about an odd index? Odd index, you can have anything you want. So, an odd index, you can have a negative or what? Positive. You know, it doesn't matter. Now, there's a couple other rules. With the even index, the answer can be positive or what? Negative. What do you mean, Hubert? Well, the square root of 25 is positive or negative what? 5. Let me explain that. The square root of 25 is equal to positive or negative 5. Why? Because 5 times 5, positive 5 times positive 5 is equal to what? And negative 5 times negative 5 is what?
Positive 25.
That's why the square root of 25 is positive 5 or negative 5. Now that you need to remember, because if you're going into 110 and 111, you need to remember that because it'll bite you on a test. So you need to highlight that. Okay? All right. Erase it. Okay. Now, look at your book. And it talks about taking the square root with a calculator. You might want to read some of these examples here. I'm not going to go over these examples. These examples are a little bit self-explanatory, page 629. And I'm not going to insult your intelligence by talking about that. Now, the plug and chug, that's basically what they're doing here. I'm not going to cover that. We've talked about plugging and chugging, and I'm not going to go into that. This right here tells you that the square root of a squared is going to be absolute value. Now, that goes against what I just said about the positive or negative. When they're asking for a square root and they tell you to make it positive, that's what they're talking about. As far as a variable goes. So if I ask you what is the square root of t squared, you're going to say absolute value of what? T, because you can't put a negative under the radical. So it has to be absolute value of a variable. The square root or the even root of a variable is always going to be the absolute value root of that variable. So what is the absolute value of r squared? What is the square root of r squared?
R.
The absolute value of r. What is the square root of x to the second power? Absolute value of x. What about the square root of x to the fourth?
Yes, the second.
Do I have to put absolute values around it? No. Why? Why do I not?
X squared.
Because anything squared is what? Positive. So you don't have to put absolute values on it. Okay? That's not really that big of a deal. Just remember, if you get an x, see here, if you get an x to the first power, you have to put absolutes on it. So the square root of x plus 1 quantity squared is absolute value of x plus 1. Well, what about the absolute value of x plus 1 to the second power? To the fourth power. Well, that would be x plus 1 quantity squared. You wouldn't have to put parentheses around that because any quantity squared is going to be what? Positive. So, not a big deal there. These are just some general rules. And there's the cube root. Talking about the cube root. And talking about how you can take the cube root of 125. I showed you that. Odd and even roots, we talked about that. I'm looking for, we talked about domain. Now, what did I tell y'all about domain? It's only affected when what? When you have a radical or a rational exponent. A rational expression or a rational equation. So, let's talk about domain of a radical. Let's say I give you f of x is equal to the square root of x plus 4. Well, right off the bat, you know, flag says you can't, the flag says a radical means domain is affected. I don't have affected. So you know right off the bat that the domain of this function is affected. So how do we find it? Always set the radicand equal to 0. Always set radicand equal to 0. Now what's the radicand? Well, the radicand is what's under the what? The radical. So you need to write that down. Now later on it's going to be called a discriminant, but it's all dependent on the context. I can say t, and if I just say t, you have no idea what context I'm talking about. I could be talking about the letter T, I could be talking about a golf tee, or I could be talking about sweet tea. There is no other tea except sweet tea. Sorry. And people that, I would like to have some unsweet tea. Shut up. All right. You're in South freaking Carolina. All right. Sweet tea is what runs in our veins.
Oh,
all right.
Actually, I went to Baltimore.
Oh my gosh.
For a vacation like a while back. And I remember talking to this lady, and we were talking about drinks and stuff like that. And she says, "Oh, what's your favorite drink?" And I said, "Sweet tea." And she's like, "Oh, you must be a Southern girl then."
Yeah.
They don't know what it is up there.
Yeah. They know what it is. They just like to make a big deal out of us down here, dumb racist Southerners. You know, they just like to make fun of us. Anyway, always said, what am I talking about? Sweet tea. There's 3 contexts that I could have been talking about. The letter T, sweet tea, or a tee that you hit a golf ball off of. There may be others, I don't know. What context? When I'm talking about just a square root, it's called a radicand. When I'm talking about x-intercepts, it's called a discriminant. All right? So it's the same thing. But this right here is your radicand. So highlight that green and highlight that green. That's your radicand. So set the radicand equal to 0 and solve. So we're going to do that. X plus 4 is equal to 0. X is equal to negative 4. Now, what does negative 4 give us in the radical?
Negative.
No. Gives us what? 0. Well, you can have 0. Yeah, that's fine. You can have 0. But now it tells you what will give you a what? A negative. Go 1 up, 1 down. All right, 1 up from negative 4 is what? Negative 3. Let's plug in negative 3. Negative 3 plus 4 is what?
1.
Negative 2 plus 4 is what? Negative 1 plus 4 is what? 0 plus 4 is 4. 1 plus 4 is 5. So we can use everything above negative 4. What do we use negative 5? What does negative 5 give us? That's not rhetorical, I'm asking y'all. Gives us a negative what? Negative 1. What does negative 6 give us? Negative 2. What does negative 7 gives us? And it goes on. So what numbers can I use? I can use negative 4 and what? And up. What can I not use? Negative 4 and what? Down. So what is my domain? My domain is all real numbers except x is, you cannot use x is less, or you just put x is greater than or equal to what? So your domain for this function is x is greater than or equal to negative what? 4. And that's how you find the domain of a radical function. Now sometimes it's not going to be x plus 4. Sometimes it's going to be a trinomial. And then you have to use, trinomial is worthless unless you what? Factor. So, let's do one. What's that? Don't you hate it when you can't find out who there it is? Okay. No, that's not it. All right, so let's do f of x is equal to the square root of x squared minus 2x plus 8. No, minus 8, sorry. All right, go to it. The reason I have to keep checking my phone is because the fellow that's coming to pick him up is a 17-year-old. And, you know, a 17-year-old, he can say he's on his way, but it takes him about 30 minutes to get where he's going. So, that's why I keep checking.
Screen.
All right, let's answer. You're a loser. I'm kidding. Don't do that. I wish I had one of those. That's a nice one.
We didn't want to get it in there.
He's got a nice scar on his arm. He decided he was going to make a trampoline out of his bed with a ceiling fan above his bed. So he's got a real nice scar. No, it did not happen at my house. It happened at his mother's house.
It was a light.
Yeah, but the ceiling fan was on the ceiling fan. How many stitches did you have to have? 3 or 4? 6?
6. There's.
Oh, it cut.
stitches.
It cut a big gash in his arm.
Yeah, it got a chunk out of it.
You gonna do it again?
Mm-mm.
Okay.
There's a couple of things he won't do. Y'all remember don't put your hand on the oven, on the stove? He decided to try to do that too.
At Gino's.
Yeah. He walked around with a white hand because it was wrapped up all the time. All right, so this does us no good. X squared minus 2x minus 8 is equal to 0. This does no good. So we've got to factor it. X and X, use your reverse FOIL.
What's your drink?
that's x and x. What else? 2 and what?
-4, or x
Well,
minus
2 and 4. And that's going to be a -4 and a positive what?
2.
I wanted him to go out this end because I can't see him down there. X, 2 and 4, and what kind of 2 we want? A negative? And what does this mean? Like or unlike? So x plus 2 is equal to 0, or x minus 4 is equal to 0. So our answers are -2, or -2 and what? So if you plug in a -2 into this function, what are you going to get? You're going to get a 0. And if you plug in a +4 in that trinomial, you're going to get, where did he go?
I never did see him out there. I was looking, but I never did see him come out. I'll be
No, I'll do it. That's fine. Okay, thank you. I don't know why he didn't come out of the bottom. He's probably, you know what he's probably
He's
doing?
probably sitting right next to the door.
Yeah, he's probably standing on it. And come on down. He's sitting there. Oh, Lord. Plug them in and see what you get. You say, where did you go? I said, end of the building. Come on down. It's down there. There he is. Okay, I finally got the two to meet up. Like, what was he doing? He's standing down there.
I was standing over next to that door. And I said, Dad, why don't you go out that door and wait on me by that table?
Thank
He
you.
said, okay. Yeah, there he goes.
Yeah. He's just standing there. Why is he standing there? Oh, my Lord.
That's the way he was at that door. He was just standing there at that door looking back at me.
Duh. I said, go down the stairs and now we'll be down there. Gotcha. Oh gosh, it takes so much communication to get a teenager and a 7-year-old to meet. All right. So, what numbers will make it negative? Well, that's where you're going to have to plug and chug. All right. So plug in a -3. -3 squared is what? 9 minus a -3 times 2 comes out, it'd be a negative. That'd be a positive what? Positive 6 minus 8. 9 plus 6 is what? That's 15 minus 8. That gives us a positive number. So -4. -4 will be 16 plus 8. So it looks like to me these are going to be okay. These are okay. How about somebody pick a number in here? What number do you think I'm going to pick? Why am I going to pick 0? Easy math, Hubert. That's right, class. -8. Can we have a -8? Nope. So we can't use anything between -2 and 4. What about 5? Let's put 5 in. 5 squared is 25. Minus 10. Minus 8. What does that give us? 25 is 35 minus 8. That's okay. Let's try 10. 10 squared is 100, minus 20 is 8, 80 minus 8 is 70. So what can you say about these guys? They're okay. So what's my domain? All real numbers, but I can't use what? Negative 2 to 4. Can I use negative 2 and 4? Yes. So it's not inclusive. So your domain is I can use negative infinity to what? Negative 2. And I can use 4 to what? To infinity. There's your domain. Question?
Can you go back to that, please?
Yes, ma'am. And that's how you check to see what numbers will give you negatives and positives. Go before the number, then between the numbers, and then after the number. And that's what they're talking about with domain and range. Oh my, look at there. Rational exponents. We've already talked about that. Exponent over what? Huh? I heard,
What?
right? Exponent over what? Number 6.
For what?
Rule number 6. What is it? Exponent over what? Index.
Index.
And that's what that's talking about on page 636. Still going over a lot of the positive rational exponents. We've already talked about that. So he's made her mad. She left. I'm looking to see what else we got here. Oh my, look at there. Law of exponents. So we're way into what? What section is that? 10.2 is coming up. No, that's 10.2. So we've got 10.1 and 10.2 covered. Now, of course, I'll be waiting on some of your questions when y'all come back. 10.3, multiplying radical expressions. Remember fractions? What was hard about fractions? Adding and subtracting or multiplying and dividing? What was hard? Which was harder? Addition. Why? Because you had to get a common what? Denominator. Multiply, you just did a cross and reduced, or canceled and did it. And what'd you do with dividing fractions? It's just multiplying by the reciprocal. So multiplying and dividing fractions is not as difficult as adding or subtracting. Same thing with radicals. Let me show you. Real simple. That's why they show it to you first. They show you the multiplying first. You know why? They don't want to discourage you. I want to discourage you, so we'll do adding first. No, I'm just kidding. I'll start with something real simple. The square root of 3 times the square root of 2. What do y'all think that is? There you go. No problem. Well, then why do people say it's difficult? Well, is there a perfect square for 6? No. So it's simple when there's not a perfect square. When it's a perfect square, you got to watch out. Let me give you an example. Square root of 2 times the square root of 8. What's that?
16.
Square root of 16, and then you're not through. There you go. All right, so we need to highlight this one. And I'm going to take my magic highlighter and I'm going to paint it red. And I'm going to highlight this because that means this is important. Whenever you have even a smidgen of a perfect square, you have to reduce. What do you mean a smidgen, Hubert? Well, is 32 a perfect square? Nope. But 16 is. And 16 times 2 is 32. See what I'm saying? So, but be careful here. Let's do one. The square root of 2 times the square root of, I don't want to do 8. Let's do just hold on a minute. I'm trying to get there. Let's try 24. All right, not a problem. Square root of what?
48.
48. All right. You're not finished. Break it up. Well, what would help you here to know your perfect squares? What perfect square? What's the biggest perfect square that goes into 48? 16. 12 is not a perfect square. 16. 16 times what? 3, Hubert. That's right, class. Y'all know what this is? This is a $5 bill. And this says you got to have what? Quarters. The 2, the square root tells you, okay, 48's fine. But that ain't what I want it in. I want it in quarters. I want it in squares, perfect squares.
So when your final answer, where did the 4 come from? Because that's the square root of 16?
You always put that out front. Now you've got to think in terms of perfect squares like that. If I say take the square root of 24, then you say, okay, that'd be 2 times the square root of 6. Well, I did 4 times 6. 12 is not a perfect square. You got to think in terms of perfect square. You're thinking in terms of dimes, you need to be thinking in quarters. And that's the key to working with perfect roots. If I put a cube up there, you got to say, okay, squares do not fit into my universe. It's all cubes. If I gave you a square root, you say, okay, cubes do not fit in this universe. This is squares. And if you don't do that, you're going to get some wrong on the test. You're going to get the square root of 8 wrong. Square root of 8 does not exist. You're going to say it's 2. And some teachers will deliberately put stuff like that on the test. I don't, but I try not to. And that's how you think in terms of the square. 48's nice, but 48's a $5 bill. You got to break it up. There's a perfect square in there. How do you know there's a perfect square in there? Because you know your perfect squares and you know your multiplication tables. And by now, by the time you get to college algebra, there's a couple of multiplication tables you should know. Like 3 times 12 is 36, 3 times 15 is 45, or 3, isn't it? And 3 times 16 is 48. You should know those. Now, that's how you multiply. Let's do a couple. Let's do a couple out of the book. Let's do a couple that they have examples. I just did one like that. All right, here's one. Here's one where you factor. I'll just do a factor. I'll just make up one. Factor square root of 300. Now, this is what you do. If you've never done this before, this is what you do. Okay, let me go back to my perfect squares. This is a square root, so I need to deal with these guys right here. Okay, everybody with me? Those guys right there. Move this over here. Now, 25 is a perfect square. 25 will go into 300. But that ain't good enough. Now, you could use 25. You just have to work extra harder. You could use those dimes in that Coke machine, but you're going to have to what? Put 10 dimes in instead of putting what? 4 quarters. So what number am I looking for to kind of make things easier? 100. 100. 300 is divisible by what? 100. You always want to go with the bigger divisor. So break that up into 100 times what?
3.
And that'll give you 10 times the square root of 3 is equal to 300. Square root of 300. Now, it's real easy. What is the square root of 3? 1.57, Hubert. Thank you, class. So what's 10 times 1.57? 15.7. Take your square root of 300 in your calculator and see if it's 15.7. Huh? 300 raised to the 0.5 power.
17.32.
Okay, well then I must have done something wrong. 10, what's the square root of 3? Oh, yeah. What's the square root of 3? I must have had 3 messed up. Raise 3 to the 0.5 power.
1.732.
Okay, I did 1.57. I don't know why I did that. So 17.32 is the square root of 300 because you take 10 and 1.7 and move the decimal one place. I'm sorry, I had a brain bubble. Now, could you have done 25? Yes. I love doing this because people go reach for the calculator. How many 25s are in 300? Well, how many quarters are in $3? I love doing that. I say, divide 300 by 25, and people will reach for the calculator. But I ask how many quarters are in $3, they say 12. Why do you reach for a calculator if you know the answer? Could there be a confidence problem there? 12
Yes.
times the square root of what? 25, right?
Yes.
And then what's square root of 25?
5.
Are we done? Nope. You still got a dollar bill here. You got to get it in terms of quarters. What perfect square goes into 12? 5 times square root of 4 times square root of 3. What's the square root of 4? 2. And what's 2 times 5? 10 square root of 3. No matter how hungry you are, you ain't going to get nothing out of that snack machine unless you get what? Quarters. You ain't going to get the right answer unless you get it in terms of what? Squares. Now, you can do them with numbers, you can do them with algebraic expressions. All right, do that one. Dang, that's loud. Can't answer that. what is this? What is x squared plus 4x plus 4?
X plus 2 squared?
It's a shortcut. Shortcut number what? Number 1, Hubert. That's right, class. What's the square root of anything squared? What happens to the radical and the
X plus 2
if
squared.
these two match up, what do they do to each other? They cancel out. So your answer is the absolute value of what? Why have I put absolute value? Because this is x to the what? First. And you can't have a negative in here, because that'd be a negative in the denominator. I mean, in the radicand. All right? Now, I want you to work on whatever you want to work on over the break. You can work on the test, you can work on chapter 7, or whatever. If you're done with all that, you can work on, what is this, 10 point what? No, this is 10.3. 10.1 to 10.3. Do not work on anything else. 7 and 10. Okay? All right, y'all get out of here. Have a good break. And be very patriotic. You live in a great country.